You the solution that I did for example 4.13 on page 155 in the book. They go through a solution, but my notes here kind of explain it a little bit more. What I want you to focus on is I want you to focus on the gained electrons and the lost electrons. And then because this is a titration, you notice down here, if we're given the volume and a molarity of one of the reactants, but only the volume of the other reactant, what is the concentration? So this is very similar to a titration for an acid base. This is a titration saying, hey, what is the molarity, or what must be this molarity if these two are going to swap electrons with each other and be the exact amount needed as gained. And that's very similar to the hydrogens to hydroxide relationships. All right, so the reaction is a 1-to-5 relationship of these two reactants. It's an acidic solution. I think by adding that, it makes this a little bit more confusing, but the hydrogens are going to help take the place of the oxygens when the oxygens leave the manganese and make some water. If you notice in the book, they only write Mn and they write Fe. We don't really care about the anions here. They could be sulfates, which mean they're spectator ions, which really, again, mean we don't care about it, but it would be nice if we would have seen some anions in there. The hydrogens, as I said, come from the acid, and when they bond with the oxygen after leaving the manganese, they make water. So the first thing I need is I need to know the number of moles of that potassium permanganate. And I do that by using the molarity and the volume. And I find that there are 2.179 times 10 to the negative 3 moles of that potassium permanganate. I then look and see I've got a 1-to-5 relationship here. And this is where you can do one of two things. You can either say, oh, 1-to-5, that's great. I can think about multiplying by 5 like we did with the acid-base titration. Or you could do something else, which I'll show you in a little bit. So as I said, with the manganese, it's a positive 7 oxidation number in solution when it's with the potassium and the oxygens. And when the liquid is purple, that tells us it's a +7. But when it's a +2, the solution turns to a light pink or even a clear looking solution color. So that is when you know the electrons are transferred. And manganese here is going to gain those electrons because we go from a +7 to a +2. The iron is the one that's going to be oxidized, or the one that's going to be giving up electrons. And we see that iron to the potassium permanganate is a 5-to-1 relationship. So for every 1 mole of the potassium permanganate, I need 5 moles of iron. Why? Because iron is only giving up 1 electron, and the manganese is gaining 5. So I need at least 5 of those to do this. So the 5-to-1 is very important. One way of doing that, now that we know the number of moles of the potassium permanganate, is we use that 5-to-1 ratio, and we find that there needs to be 1.090 times 10 to the negative 2 of iron sulfate in that 25 milliliters. And if I'm trying to figure out concentrations, I need to put it over the number of moles over the volume of 25 and relate that to if I had 1,000. So by doing that, I get 0.436 big M. Or what we did with the acid-base titration, we can say, hey, 5-to-1 relationship, I'm going to take my big M for the potassium permanganate, I'm going to multiply it by 5, and I'm going to use that and set it up as an M1V1 equals M2V2, and my M2 is that unknown concentration. And the unknown concentration, not surprisingly, when you do it this way, is also 0.4360 big M. So 2 ways of thinking about it: how to get the number of moles of the iron sulfate when you have 25 milliliters. It's all about the number of moles that you have, especially because of the milliliters and the molarity, and then trying to figure out the number of moles you have in that 25 milliliter, knowing a 5-to-1 relationship. I hope that helps. We'll talk a little bit more about this on Wednesday during class.